Look at any major city after dark. Every lit window and functioning server relies on a continental network that must maintain a perfect balance of frequency and voltage every single second. We treat this supply as a static utility, but it is an incredibly delicate engineering feat. On a Friday afternoon in August 2019, a single lightning strike hit an overhead transmission line in the United Kingdom. Lightning strikes the grid constantly, but this time the shock caused multiple generators to trip offline simultaneously. Within 45 minutes, the disruption compounded. Software lockouts paralyzed commuter trains on the tracks, traffic lights went dark, and over 1 million people lost power. Charles Perrow's normal accidents framework suggests that in these tightly coupled systems, the interconnections themselves create a new category of risk. When components are this interdependent, a single failure can bypass traditional safety layers. The UK event revealed a systemic vulnerability. As our grids become vastly more complex, localized anomalies can trigger widespread cascading failures that outpace existing defenses. Sometimes the trigger is raw physical force. In February 2021, severe winter storms pushed the Texas grid far beyond its design baselines. The extreme cold froze natural gas wellheads and water infrastructure, cutting off fuel to power plants exactly when heating demand reached record levels. This flowchart maps the 2016 South Australia blackout. 6 rapid network faults forced multiple wind farms offline. With generators gone, power surged through the Haywood interconnector. It overloaded, and automatic protection severed the tie, isolating the region and causing a total system collapse. But modern grids can also collapse without a single broken wire. On April 28, 2025, the Iberian Peninsula lost 15 gigawatts of generation, roughly 60% of its total demand, in only 5 seconds. The culprit was a machine-driven error, subsynchronous electromagnetic oscillations. In an inverter-dominated grid, small voltage fluctuations amplified out of control, causing a rapid sequence of overvoltage disconnections. Whether the trigger is a physical storm or a digital oscillation, the tightly coupled architecture ensures that one failed node transfers its entire electrical load to the next. The loss of electricity immediately impacts the basic infrastructure of a community, halting the services required for safety and healthcare. During the 2019 Venezuelan blackouts, hospital life support systems failed and public transportation stopped. Without power for pumps, citizens were forced to collect water from contaminated runoff streams. To reverse a collapse, operators in control rooms must orchestrate a black start. This is a precise process of resurrecting a dead grid from scratch, without relying on any external power supply. After the Iberian collapse, operators leveraged hydroelectric and gas plants to create localized pockets of electricity, functioning as isolated power islands. Engineers then spend hours synchronizing the exact frequencies of these volatile islands, linking them together to bring the regional network back online. But this recovery is a reactive process. As grids move toward fast-acting renewables, manual human intervention is often too slow to catch collapses that occur in milliseconds. This creates a transition paradox. Moving to cleaner, renewable energy is necessary to reduce carbon emissions, but it removes the primary stabilizing force that once protected the grid. Traditional fossil fuel plants provide rotational inertia. The physical momentum of these heavy, spinning steel turbines acts as a shock absorber. If demand spikes, that kinetic energy resists the drop in frequency, buying the system time. To replace this, engineers are deploying grid-forming converters. These devices use energy storage and smart software to digitally inject voltage control, providing synthetic inertia that maintains stability in real time. Utilities are also integrating artificial intelligence to act as a sentinel. These models analyze thousands of noisy data points per second to isolate local faults fast enough to stop a cascade before it can spread. Surviving the energy transition requires us to move away from passive stabilizers. Keeping the lights on in the 21st century demands that we actively govern the millisecond-to-millisecond chaos of the network.